Hi there, and welcome to our lecture on acceleration. This is motion 2 of Unit 5. Our key ideas: what changes when an object accelerates? How do you calculate the acceleration of an object moving in a straight line? And how can we graph be used to find acceleration? So beginning to look at that first question, when an object undergoes acceleration, its velocity is changing. So we can define acceleration, the rate at which velocity changes over time. An object accelerates if speed, direction, or both change. So if we speed up or slow down, acceleration changes. If we turn around a corner, but we're keeping the speed the same, acceleration will change. Or if we're slowing down and making a corner, acceleration is changing then too. Another example is if we were to spin something around in circles, the acceleration is constantly changing. Even if we're spinning at the same rate, because the direction is continuing to change, acceleration is continuing to change. So acceleration can be a change in speed, increase or decrease. In speed is acceleration. We use the word acceleration for decrease and increase. In physics we do. Acceleration can also be a change in direction. So a motorcyclist who rides around the inside of a large barrel is constantly accelerating. So we've got the motorcycle going around in circles. A person riding on a Ferris wheel at an amusement park is also accelerating because direction is changing. The acceleration of these circular paths, because they're in circular motion, is known as centripetal acceleration. Another quick note: if we were to note acceleration as increasing or decreasing, we tend to use a positive sign if it's increasing in acceleration, or we use a negative sign if it's decreasing. If it's slowing down, we use a negative sign. So how can we calculate the acceleration of an object moving in a straight line? The average acceleration over a given time interval can be calculated by dividing the change in object's velocity by the time over which the change occurs. So not only does it sound complicated in words, it looks a little complicated in formula form as well. So our acceleration here is just a change in velocity. So we take our final velocity minus the velocity we're initially going, and we divide it by time. So if we were at a stop sign waiting for traffic to clear, our initial velocity would be 0 meters per second, and then however fast we accelerate to, say we accelerate up to 20 miles or 20 meters per second. So our initial would be 0, so we just have 20 divided by how long it took us to go from up to 20 meters per second. And we denote this in symbol form. Velocity, we use V or A. Acceleration for A. Velocity is V. We do a subscript F for final velocity. We subtract that off the initial velocity, so we use V, and then we use subscript I to indicate initial. Sometimes you'll see a 0 instead of the I. This means the same thing. And we divide by time. This simplifies down to change of velocity, and we've got a symbol that's missing here, so we've got a delta. Use Greek letter delta to indicate that there's change that's occurring. So change of velocity divided by time, and sometimes we put a delta in front of t as well because we want to know. Sometimes we have to figure out how much time it takes to, so we might have a delta t here as well, just to indicate that time changed too. So acceleration is the rate at which velocity changes. In this book, and actually many books, straight line motion is indicated as a positive acceleration, meaning the velocity, or meaning that object's velocity is increasing when the object is speeding up. So use a positive symbol. Negative acceleration or deceleration means the object's velocity is decreasing or the object is slowing down. We use SI units to indicate acceleration, and because velocity is meters per second and acceleration is per unit of time, we do meters per second, which we can show as meters per second. We can show as this. We can show this notation. However, meters per second squared tends to be more of the universal notation of how we show acceleration meters per second squared instead of meters per second. We just multiply these seconds together and get seconds squared. Alright, so looking at a math scale here, we've got a flower pot that falls off a second story windowsill, sorry. The flower pot starts from rest and hits the sidewalk 1.5 seconds later with a velocity of 14.7 meters per second. So we want to find the average acceleration of the flower pot. We're going to list what we know and what we don't know. So we know the time it takes is 1.5 seconds. So we can call this final time if we wanted to do some math for time as well. But we don't have to. So it takes 1.5 seconds to get there. The initial velocity, because it was at rest, so our key word here is rest, it's 0 meters per second. The final velocity right before it hits the ground, because obviously when it hits the ground it's back at rest again, but just before it hits the ground it's at 14.7 meters per second, and we have a directional term here because we're still dealing with velocity. We need to know what direction it's going. So we want to know what the acceleration was. The direction is down. But what was the acceleration right before it hit the ground, or actually the acceleration, the average acceleration through the entire fall, and what does that end up being? So we're going to write our equation out. So we've got acceleration equal to final velocity minus initial velocity divided by the time. So we're going to insert what we know. We know 14.7 meters per second is our final velocity. Subtract off 0 from 14.7, so we still have 14.7 divided by 1.5 seconds. So we end up with 9.8 meters per second squared down, which interestingly enough, this is also the acceleration due to gravity, which we'll get to later, so you don't have to worry about that right now. And another way that we can indicate down here is writing 9.8 meters per second squared as a negative number. So negative also indicates down. Alright, so how can a graph be used to find acceleration? The slope of a straight line on a speed time graph is equal to acceleration. Notice this is different than our velocity graph. Velocity was distance time. Now we've got speed, or velocity versus time graph. So we can use velocity as a term here as well, so we'll just write that in real quick. Maybe. Guess there it goes. So velocity, or speed, versus time is going to give us acceleration. So the graph looks a lot alike, so you're going to have to pay attention and be careful to what the y-axis is labeled as. So this is your key here, the y-axis, or your dependent variable, because our independent or x-axis is the same. So make sure you pay attention to this y-axis. So speed versus time gives us an acceleration. And we'll see in a minute here that when this line decreases or goes down, we've got a negative acceleration or deceleration. We're slowing down on that particular graph. We can see acceleration on a distance time graph as well. And when we were to, if we were to put this on a distance time graph, we're going to see acceleration as a curve. So if we had a straight line on distance time, actually it would be speed or velocity. So this curved line indicates there's acceleration. So the change in velocity is changing at most points along this line. Okay. So distance versus time graph is not a straight line. Velocity is not constant. Therefore, acceleration is taking place. The curved line indicates an object is under acceleration. So looking at a graph example or graphing example to use a graph to figure out what acceleration is. We've got a bus traveling on a straight road at 20 meters per second uniformly slows down to a stop over 20 seconds. The bus remains stopped for 20 seconds, then accelerates at a rate of 1.5 meters per second squared for 10 seconds. Then continues at a constant speed. Graph speed versus time for 60 seconds. What's the bus's final speed? So there's a lot going on in this problem. So we're going to determine the x and y axis. The x-axis is always, or most of the time, it's time. It's measured in seconds. The y-axis is speed. So we use v, and we're measuring in meters per second because we want to know speed or acceleration. So you're going to start from the origin and graph each section's motion. We're going to draw and connect the first 2 points. So we're at time 0. We're here at the x-axis. We're at velocity 20 meters per second. So our first point will technically go there. Let me draw those in. So here's our first point. And then we're at time 20 seconds, velocity 0. So here's our initial deceleration. The bus is slowing down at a constant rate because we have a straight line here from 20 meters per second to 0. So it comes to a stop. We're drawing a horizontal line while the bus was stopped. So notice that our line is along the x-axis. So time continues, but we're not going up into this velocity section. So we go from 20 seconds to 40 seconds. And then at 40 seconds and speed 0, so at the bottom point here, we're going to draw a line with a slope of 1.5 meters per second squared. So that indicates our acceleration, this 1.5 meters per second squared acceleration. And we can figure out the acceleration. So we have 1.5 meters per second. So how many meters would we have to get? 5, 10, 15. We go 10 seconds. So 15 divided by 10 gives us 1.5. So that's how we get this slope. And then our last part is draw a horizontal line from time 50 seconds to 60 seconds and at velocity of 15 meters per second. So if we look at the graph, we can read it and figure out what is our speed at 60 seconds, and it's 15 meters per second just going across to the y-axis. So thanks for listening.